All right, for real this time. All right, so as Roland said, I'm talking about Monte Carlo neutrino transport. And this is work that I've done with my advisor at Caltech, Christian Ott, and some collaborators. Hiroki Nagakura is a postdoc at Caltech, and Kosuke Sumiyoshi and Shuichi Yamada have worked on this discrete ordinate solver that I will be comparing against. This picture on the front is a benchmarking example of Monte Carlo radiation transport in a three-dimensional core-collapse supernova model. So I want to start by explaining what a core-collapse supernova is and hopefully motivate that doing this very detailed radiation transport is a fundamentally important problem for core-collapse supernova theory. So just to orient people who aren't supernova theorists, the idea behind a core-collapse supernova is when a star something like 10 times the mass of the 10 times the mass of the sun or heavier will eventually collapse under its own weight. And this core will, once it reaches nuclear densities, about a few tenths of a second after the onset of collapse, will reach nuclear densities. The strong nuclear force will kick in and cause the core to bounce back outward a little bit. And this bounce sends a shock wave moving through the rest of the star. And that's what you see here, is there's a shock wave moving through the supersonically infalling matter around it. There's in these core-collapse supernovae that we observe, there's something like 10 to the 51 ergs of energy, of kinetic energy that come from these explosions. However, we also know that the amount of neutrino energy emitted from these is something like 10 to the 53 ergs. Now, simulations have showed us that shortly after this collapse, although a shockwave gets sent out, within a few tens of milliseconds, the shock stalls, and is not able to push past the very quickly infalling outer matter. So the main thrust of core-collapse supernova theory is trying to figure out what mechanism actually causes this shock to revive. And it's important to note that this shock is at a very tenuous position. It's right at the boundary between just collapsing back in on itself and actually exploding through the star. So very small effects in how the neutrinos change lead to large effects in whether the star explodes or not. So the canonical theory, as I alluded to, is that there's neutrinos that are emitted from this dense inner core. They pass through this matter that's under the shock, and as they're passing through it, they deposit a lot of energy, drive turbulence, and this drives the shock wave outward. Because neutrinos are so fundamental to this process, and it's so tenuously sitting between exploding and not exploding, treating these neutrinos accurately is very important. So neutrinos are, although I won't be talking much about neutron star mergers, it's interesting to note that it's also very important for neutron star mergers. So with a neutron star merger, you have two neutron stars or a neutron star and a black hole that are orbiting each other, and one or both of these neutron stars will be tidally shredded and launch out some dynamical ejecta, which is thought to be the origin of most of the universe's very heavy elements. The remaining matter will form a accretion disk around some central black hole or neutron star. And this accretion disk is very hot, and it's emitting a lot of neutrinos. These neutrinos can drive an additional wind out from the disk, which affects what kinds of elements we expect to be formed from these mergers. There's also one idea that neutrinos emitted from this disk can annihilate in this region above the merger accretion disk and drive a hyperrelativistic jet. So the question behind this is can these sort of basic conceptual models actually pan out in detailed computational models? And of course, to do this correctly, you need very detailed neutrino transport. So what exactly is a neutrino? So just to give a sense of scale, a neutrino is a very small, very weakly interacting particle. A sort of canonical cross-section is something like 10 to the minus 44 square centimeters. So just neutrinos coming from the sun, there's a couple 100 billion passing through you every second of the day and night. So they're very, very weakly interacting. But when you get densities that are as high as we see in core-collapse supernovae and in neutron stars, the neutrinos actually interact pretty strongly and can even be completely trapped inside of the fluid. Fortunately, neutrinos, unlike photons, are relatively simple in their interactions. There's a small number of things they actually do. We don't have to worry about resonance lines or anything. They move in straight lines at about the speed of light. They are much too much too light to be thought as any subrelativistic particle. So they're moving at the speed of light. Neutrinos can absorb on nucleons. So in this case, an electron neutrino is absorbing onto a neutron, and that turns a neutron into a proton and deposits a lot of energy. Neutrinos can also scatter off of electrons and protons, and this helps redistribute the radiation energy and can trap the neutrinos. And finally, neutrinos can also annihilate against themselves and create an electron-positron pair or some other lepton pair. And this serves to deposit lots of energy. So radiation transport in general can be described by this Boltzmann equation, which describes the evolution of this quantity F. And this is a pretty important quantity in radiation transport. It essentially describes the number of neutrinos per unit volume that are moving in each direction and that have a given energy. So there's 6 dimensions plus time. So anytime you want to double your resolution, the cost of simulation increases by a factor of 2 to the 7. And of course, detailed calculations include lots of other physics, including, these systems are really, truly 3-dimensional. We have to treat them with general relativistic, sometimes magnetohydrodynamics. There's a complicated nuclear equation of state that goes into it. There's nuclear reactions that determine what elements we get out of it. But I'm just going to focus on this one small component, the neutrino radiation transport. So, like I mentioned, the neutrinos are a very fundamental process or a very fundamental component of these large simulations. So it's very important to actually make sure that we are treating them right. So of course, all simulations on some level are incorrect, and our ability to extract valuable information from these simulations depends on how accurately we can determine how much realism is in these simulations. So the goal, one of my goals is to provide some kind of benchmark via open data and open source software that the community can use to ensure the accuracy of this very fundamental process in their simulations. So I'll talk specifically about 2 methods that do the exact same thing. They both solve the transport of radiation through these systems. Radiation transport schemes are broadly categorized into 2 categories. There's deterministic methods, where you create some kind of grid or to discretize the radiation field, and you evolve that forward in time. The other is some kind of probabilistic method, where you treat individual particles, and it's random as individual particles actually are. So on the left, this is an example of the former case. It's called discrete ordinates because at each point in space, your radiation field is discretized into bins. So there's some number of bins for every direction that a neutrino can move, and also bins for the neutrino spectra. So the energy of the individual neutrinos. And so there's a value for each one of these grid zones, and you evolve all those forward in time. The other method is Monte Carlo neutrino transport, where you choose a random location according to the emissivity of the matter. You spawn a particle with a random direction and with a random energy according to the emissivity, and that particle will move a random distance according to the opacities, and scatter and scatter until it eventually escapes or is absorbed. And so if you do this some number of billions of times, you get a pretty good idea of what the distribution function at each point in space looks like. So the key challenge with this kind of method is that treating radiation in full generality is very, very expensive. So on the left-hand plot, I have so of course, every method has its own strengths and its own weaknesses. And so on the left-hand side, I'm sort of exposing one of the weaknesses of the discrete ordinance method. That is that it's very diffusive. So this black line is a very high-fidelity Monte Carlo simulation in a one-dimensional core collapse snapshot. And this black line can more or less be thought of as the actual answer. All of the other lines, so these dotted lines are discrete ordinate simulations. So this blue line is a low-resolution simulation, the green line is a medium one, and the red line is a high-resolution simulation. So you can see that it requires very high resolution to approach this ideal result. And the reason behind that is that you can only use a finite number of angles. So if you want to, so this quantity here represents how forward beamed the radiation is. So here the radiation is all moving in every direction because it's all trapped, and at the edge it's moving all in one direction, just outward. So because the discrete ordinates method has a finite number of bins, it has difficulty reproducing this one direction movement unless there's very, very high resolution. And in general, with this discrete ordinate scheme, in supernova simulations that have been done in the past, this low resolution line is about the limit of what can be done for 2- or 3-dimensional simulations. Now, of course, Monte Carlo, although it has exquisite angular information, its problem is that it is, in general, very noisy. So you have a random number of, each of your individual particles does a random thing, but in order to get an idea of what the full distribution looks like, you need to simulate a lot of these particles. So this is, again, the benchmarking 3-dimensional simulation. The color plot here is logarithm of the energy density. But the main point is you can see that there's a lot of noise. It's not clean. You can see there's a couple of individual particle trajectories that you can see that are going through this slice. And so in order to have a really well-resolved 3-dimensional calculation, you need to do this essentially something like 10 to the 5 times of what's shown in this picture. And just for a sense of scale, this 3-dimensional calculation is something like 1 or 2 node hours on blue waters. So for a single 3-dimensional calculation, you need something like 10 to the 5 node hours for each time step. So my goal was, of course, to verify that both these methods are converging to the same result so that we can be sure that both of them are producing the correct result. So Blue Waters is enabling, for the first time, this is done in a multi-dimensional sense. This has been done in the past in one-dimensional codes, but this is the first time that it's done for a multi-dimensional problem. So the discrete ordinate scheme we use is written by Hiroki Nagakura and the 2 other people I mentioned before, Yamada and Sumiyoshi. And for a sense of scale, this was run on the Japanese supercomputers, the one-dimensional cases on FX and on the Japanese supercomputer K. And they use something, so the 1D simulations use something like 70,000 core hours, and the 2D simulations something like 9 million core hours. And in contrast, the Monte Carlo simulation, I designed this code and run it on Blue Waters, and it uses something like 6,000 core hours for 1D and something like a few 100,000 core hours for 2-dimensional calculations. And now, in order to sort of remove all other effects, we just use the same opacities and we apply it to the same static background snapshots. So this is what we get. On the left side this is a plot of the neutrino energy density as a function of radius. This right here is the supernova shock radius. Below here, I mentioned that neutrinos can be trapped. All of these neutrinos are very isotropic and trapped. But eventually, the density gets low enough that they become free streaming, and there's this semi-transparent region, which is pretty difficult in general to resolve. And this plot always makes me very happy. This is the highest resolution simulations for the discrete ordinates and a lot of Monte Carlo particles, and you see that they converge very nicely to essentially no error. And of course, the error that is there, you can drive it down by increasing the number of particles and by increasing the discrete ordinates resolution. And just to give a sense of what the distribution function looks like, this is sort of the shape of it. So this values moving this direction, this is the radial direction. So this is something like 35 kilometers, which is somewhere around here. So it's pretty isotropic at around 35 kilometers. But as you move outward, it's very forward peaked. And again, the discrete ordinate simulations and the Monte Carlo simulations show very, very good agreement. So we can consider that verified. Now, of course, we're doing this in 2 dimensions also. So this is a 2-dimensional plot of this quantity PR theta, which doesn't exist in 1-dimensional calculations, but this is a sensitive probe of how anisotropic your radiation is. And this is, in general, a pretty difficult thing to resolve because there's a lot of subtractive cancellation. So like I mentioned, Monte Carlo is noisy, so the simulation is still in progress, and so as the simulation runs, the noise will be driven down. But we already see that there's very good agreement between the two, and most of the noise, or most of the error, is just random noise that will be driven down with increasing simulation time. So we see very good agreements in all of the metrics that we're using, so we're very happy with the what we believe is the realism of both of these codes. So now, of course, there are a vast variety of other methods. So I'm going to talk about one here, this two-moment method, or any number of moment method, which is an approximate way of treating radiation transport. Essentially what you do is, instead of evolving this distribution function f, you evolve moments of f. So the 0th moment is the energy density, the first moment is the flux, the second moment is the pressure tensor. There's an infinite list of these that you can simulate if you really want to. But with these truncated moment methods, you cut it off at some point. You say, I'm only going to simulate the energy density and the flux, and I'm going to pretend that I know what the pressure tensor is. So we can use these, the idea is that we can use these very accurate simulations to sort of both assess the accuracy of these approximate methods and to inform these approximate methods to make much more reliable simulations in the future that are, have the accuracy comparable to the higher order methods with the speed that these low order methods provide. So just to give an idea of how well they compare, this is, again, this radial RR component of the pressure tensor. And the errors, so this is the black line is the Monte Carlo result, and these lines, the other lines are what is predicted by this approximate scheme. And the errors are pretty acceptable, but they could be driven down by using Monte Carlo simulations to inform what these higher order moments are. And just to give the same sort of thing in 2 dimensions, this is the R theta component of the pressure tensor, which is the one that said that only exists in 2 dimensions. And so there's, again, very good agreement, but there are regions where this approximate method struggles, and we can, in the future, provide insight on how to improve these methods. And I won't talk about this. This is a method that made these Monte Carlo simulations possible, and it's, I find it very interesting. If you'd like to talk about it, talk to me more about it after the talk. But in short, the Blue Waters Fellowship has enabled me to develop a rigorous, develop new methods for Monte Carlo transport and provide rigorous verification of these methods, as well as other things that I'm working on to feed this back into dynamical methods, or dynamical simulations. The Blue Waters hardware is very well suited for these parallel Monte Carlo radiation transport simulations. The support staff for Blue Waters has, of course, been instrumental in optimization and implementation ideas for these new methods. And the hope is that this open source code and open data will help benefit the community by providing a much more easily accessible verification tool. Thank you.
Okay, we're actually